Okay, so picture this. You have to build a skyscraper, but you have to do it in the middle of the ocean during a storm. Sounds impossible, right? Well, that's pretty much the challenge engineers face with offshore wind turbines, and the solution they've come up with is just brilliant.
And I'm not exaggerating about the skyscraper part. To really get a sense of the scale here, a single one of these turbines can be over 850 feet tall. We're talking blades longer than a football field. These things aren't your friendly neighborhood windmills. They're absolute giants, standing up to the full, raw power of the sea.
Which, of course, brings us to the big question. How in the world do you anchor something that massive against storms, constant waves, and a seabed you can't even see? Especially when you can't just bring in a giant city-sized hammer to pound it into the ground. Well, the answer is one of the coolest tricks in modern engineering.
It's called the suction bucket solution. And yeah, it's pretty much what it sounds like. It's this revolutionary idea that takes the ocean's incredible pressure, the very thing that's trying to destroy the turbine, and turns it from an enemy into an ally, using it to lock the whole thing down.
Now, the official engineering term is a suction-installed caisson foundation, or SICF. I know that's a mouthful, so let's just break it down. A caisson is basically just a big, hollow, watertight box. In this case, it's a giant steel can, open on the bottom. The real magic starts when you place it on the seafloor and start pumping the water out of it.
The absolute best way to think about it is like an upside-down bucket. You know, if you take a bucket, flip it over, and try to push it into wet sand at the beach, that suction you feel helps pull it in and holds it tight. Now, just imagine that bucket is the size of a building. That's the core idea.
And what you're seeing here are the two main ways they use this tech. Sometimes it's one single, massive bucket holding up the entire turbine. Or, like in this picture, you use 3 or 4 of them as the feet for a bigger, lattice-like structure, creating this super stable tripod right there on the ocean floor.
So, how do they actually pull this off? Well, long before any of that steel even touches the water, you have to create a perfect map, a blueprint of the seabed. You can't just drop this thing anywhere. I mean, we're talking about $1 billion piece of hardware. Picking the wrong spot could mean a tilted turbine, or worse, a total catastrophic failure.
It's this super careful 3-step process. First up, a geophysical survey. That's like using sonar to map out the hills and valleys of the ocean floor. Second, a geotechnical survey, where they actually take samples to figure out what the seabed is made of. Is it soft clay, sand, or hard rock? And finally, they mash all that data together to build a super detailed 3D model of the ground.
And what they're looking for is fascinating. It's not just about finding a nice flat area. They are on a treasure hunt for hidden dangers. We're talking about giant boulders hidden under the mud, unexploded bombs from old wars, seriously, or a surprise layer of rock just below the surface. Any one of these could cause that giant foundation to land crooked, turning this massive project into an incredibly expensive disaster.
And the precision here is just nuts. It's like a surgeon planning an operation. For a foundation with multiple legs, you can see they plan out tests for the exact spot where each leg is going to land. Every single one gets its own personalized investigation to make sure everything is perfect.
All right, so the blueprint is done, the spot is greenlit. Now comes the main event, the most dramatic part of the whole process, the installation.
So, if you're not using a giant hammer, how do you get this colossal steel bucket to sink deep into the seabed?
It happens in 2 main phases. First, a huge crane carefully lowers the foundation down to the seafloor. Just its own incredible weight is enough to push it a few feet into the soil, which creates a nice seal. Then, phase 2 kicks in. The pumps fire up and start sucking the water out from inside the bucket.
And this diagram shows the pure genius of it all. As the water gets pumped out, the pressure inside the bucket drops like a rock. Suddenly, the crushing weight of the entire ocean above it is pushing down. The pressure from the surrounding soil is pushing in. All that force smoothly drives the foundation deeper and deeper. Get this, you're not pulling it in. You're letting the ocean itself do all the heavy lifting for you. But this also creates a huge risk. That immense external pressure could actually crush the steel walls inward. But, getting it in the ground is really only half the battle. Now, that foundation has to sit there for decades and survive everything the ocean can throw at it. We're talking hurricane winds, monster waves, and the constant attack of corrosive saltwater.
And making sure it survives requires a level of precision in the math that is just mind-boggling. Every single variable, from how dense the clay is to the maximum height of a wave in a 100-year storm, has to be calculated with almost perfect accuracy.
To give you a little peek behind the curtain, check out this debate from an actual engineering forum. They're arguing about how precise is precise enough. Some of the software they use is incredibly strict. If just one data point out of a million is a little off, it flags the entire design as a failure. Other software is more forgiving. This isn't just nerds arguing online. This is a high-stakes decision about what perfect really means when a billion-dollar structure is on the line.
So, what are they even calculating? Well, they're modeling all the forces you see here. It's not just about surviving that one massive wave from a freak storm, which could just snap it. They also have to calculate the effect of millions and millions of smaller, repetitive waves and wind gusts that happen every day. It's like bending a paperclip back and forth. Eventually, even small forces can cause it to break.
So they have to design for different kinds of failure, what they call limit states. The ultimate one is about surviving that one single catastrophic event. The fatigue one is about surviving that paperclip effect over 25 years. And the serviceability one is to make sure the turbine doesn't just start tilting or sinking over time, making it useless. To get built, it has to pass all three of these tests.
So, after all of this absolutely incredible engineering, what does it all really mean for us, for the future of energy?
Well, it means that a pretty simple, ingenious idea, literally an upside-down bucket, has been scaled up and engineered to perfection. It's become a key piece of the puzzle in our shift to clean energy. It's quieter to install, it's faster, and it's helping us unlock the truly immense power waiting for us out in the world's oceans. This is the kind of incredible engineering that's making massive clean energy projects a reality, right now. It takes a huge problem and solves it with a stunningly simple solution. And it makes you wonder, right? As our need for energy keeps growing and we have to push into even more challenging environments, what other impossible structures are we going to have to invent tomorrow?